Welcome everyone to this exciting masterclass today on nonlinear partial differential equations. So we'll be focusing on understanding the complexities and intricacies of modeling nonlinear phenomena in nature. And this is a well-known fact that solving nonlinear partial differential equations, which are the models for many of these phenomena, is often an impossible task. So during this masterclass, our goal is to give you a deep understanding of the techniques, modern techniques on partial differential equations, such as existence, uniqueness, the behavior of solutions, and we'll cover a wide range of topics. And we'll start with my lecture on the connections between Hamilton-Jacobi equations and reinforcement learning, nonlinear wave propagation, hyperbolic equations, Fourier analysis in music, and the last lecture tomorrow will be even on a visual guide to PDE models. So I really hope that by the end of this masterclass, you have a new appreciation for the beauty and complexity of PDEs and their solutions. And at some point, if you would like to continue your research in this area or start your research in this area, maybe you can think of KAUST as one exciting venue to do so. Today I'll be talking between the connection between optimal control and machine learning, and in particular reinforcement learning. This will be certainly an introduction. In half an hour there is no way I can tell you everything about these topics. Each of them is certainly more than one semester university course, but I'll start at least with some key ideas. And the optimal control problem, and what we are doing here is called the terminal value in optimal control problem, is the following. You have a time horizon, terminal time, you have an initial state, and you have some dynamics that you control. So the objective is you want to choose a control, and the goal is to minimize a running cost. So this is the running cost, and added together with the terminal cost. So terminal cost. And so X is called the state and A is called the control. And this problem arises quite often in many engineering problems. And a typical example is the linear quadratic control problem, where you have A, B, C, M, and N. These are all positive definite matrices, for example. And you may want to stay close to the origin, so you penalize for large x's. You don't want to use very large controls, so you penalize for large controls, and you penalize for large terminal states together with a linear dynamics. And this is the linear quadratic control problem, which will come back as an example multiple times during this lecture. Now, if you start thinking and say, well, look, I would like to find this optimal trajectory. So I would like to find the best possible trajectory that minimizes the running cost plus the terminal cost. And you ask, well, what are the necessary optimality conditions? So what must happen for a trajectory to be an optimal trajectory? And it turns out that there is something called the Pontryagin maximum principle, which characterizes these optimal trajectories. And the idea is the following, well, first, an optimal trajectory must satisfy the dynamics. So this is satisfy the dynamics. Then there is an additional auxiliary equation called the adjoint equation. And this is a linearization. If you think about this, this is kind of a linearization of the dynamics around the state. And then there is a final condition that your control maximizes a function that combines the dynamics and the running cost. And this is called the Hamiltonian and you'll see why Hamiltonian. So if you give me a trajectory, and if this trajectory is optimal, then it satisfies three conditions. One, satisfies the dynamics. Second, we introduce an adjoint state, and given this adjoint state, then there is some maximality property of the control. Control is chosen in a particular way. And the connection between this and something that many of you may know, the Hamiltonian dynamics, is this calculus of variation setting, where your dynamics, you control directly the velocity. Then if you introduce the Hamiltonian, which is the Legendre transform, this is actually the classical mechanics Hamiltonian, and this is the Legendre transform of the Lagrangian, then what you have is, if you look through the algebra, before the necessary optimality conditions become the Hamilton equations, and these are equivalent to something that some of you may know, which are the Euler-Lagrange equations. So if you try to minimize this integral of L of x dot, so you're controlling the velocity, then you have a necessary optimality condition, which is this one, and this turns out to be equivalent to the Hamilton's equations. So we have a way to decide whether a certain trajectory is a candidate for optimal trajectory, and in particular, if you go back to this linear quadratic case, if you take the quadratic Lagrangian, a little bit of algebra will show that the corresponding Hamiltonian is this one, is the Legendre transform of the Lagrangian, and this is minus dph, and this is dxh. So, and if you look at what this means by differentiating this equation, you get the harmonic motion. Okay, very well. So we have, if we're looking at optimal control, the first thing that we do is that we look at trajectories, and we ask what are the necessary optimality for these trajectories. And the take-home message is that there is something called the Pontryagin maximum principle, which gives you necessary optimality conditions. And in particular, for linear control problems, we recover fairly well known differential equations. And if you look at optimal control and you ask what is there to be studied, well, certainly the first thing is, do we have optimal trajectories? And maybe one thing is sufficiency of necessary conditions. So what I mean by this is, can we prove that if I have a solution to Pontryagin maximum principle, it's a minimizer? And it turns out that under convexity conditions, this is true. Can we compute optimal trajectories? Well, we can compute them if we have, for example, that Pontryagin maximum principle gives you a sufficient condition for optimality. And then there is a number of other issues, such as like controllability issues. Can I find a control that takes my trajectory to a given point? There we go. Now, there is a different point of view, which is the point of view of Hamilton-Jacobi equations. And the idea there, and let's do this in the calculus of variation setting, is to look at this control problem, and rather than focusing on the trajectories, focusing on the value function, which is the best you can get for this control problem here. Of course, this is a function where the infimum is taken, for example, over C1 trajectories, and then you can ask, well, can we do something with this function? Well, it turns out that the first thing that you prove is something called the dynamic programming principle, which is the following thing: is if you have a time horizon t and t plus h, and here you know the value function, then you can compute the value function here by just trying to find the best trajectory that combines the short-term running cost plus the rest of the running cost plus terminal condition. And the way that I like to explain this is the following, is that if you want to go home in the shortest possible way, you go in the best direction and you keep going in the best direction. So you go from here to here, here to here in the best possible way, and then you go in the best possible, and you can continue in the best possible way. Why this is useful? Well, because see, if you have an analog to this problem is the following. You are given, let's say, a graph, and you want to find what is the shortest path between end and beginning. And if you try to enumerate all paths, then this is very expensive because there are lots of paths, and this is a simplified situation, but certainly some paths are really bad. For example, I mean, you certainly would not try to loop around like this and then go back and then go to the end. So there are some paths that are clearly suboptimal, but there are paths that are not optimal like this one that you would have some time ruling them out. So the way you approach this problem in dynamic programming is this. You say, well, if I am at the end, I'm at zero cost to the exit. If I'm here at the cost 1, if I'm here at the cost 2, here I'm at the cost 3, because I can move there or I can move there. Here at cost 4, here at cost 4, here at cost 5, and here also at cost 5. And so you can, out of this thing, figure out that this trajectory here, for example, this one, and this one is an optimal trajectory without having to enumerate all paths. Now, if you want to characterize the value function, then you look at something called the Hamilton-Jacob equation. And the idea is that assume that everything is nice and differentiable so that this guy can be expanded in Taylor series near x and t, and that this integral can be approximated by just a simple quadrature rule. Then if you have this approximating property, this u cancels with this u, and what you get is, in the best possible case, you get the Hamiltonian plus ut, and from which you deduce this Hamilton-Jacob equation. Of course, this is a formal derivation. What can be done rigorously is something called the verification theorem, which is this: if L is uniformly convex and you have a solution to the Hamilton-Jacob equation with the corresponding terminal conditions, then U is the value function, and out of this value function you can actually build an optimal dynamics in feedback form. So this is optimal dynamics in feedback form, meaning that for every x and t, you know exactly what the x dot is. Now, this is not that different from what we did here. You see, what I did in this example here was to say, well, look, if I'm here, where should I move? So if my distance here is 5, I want to move to a point where the distance is smaller than 5, which is this one, right? And I'm here at this 4, where should I move? Well, if I move to this 4, that's suboptimal, because then I move 1 and then still have 4 to go in the best possible way. So what I do is that I'm at this 4, I move to this point, which has a distance 3 to the exit. And then, well, here I could also move to this guy because it's the same, right? The cost here and the cost there are the same. And then I could move to this one, for example, I could move to this one. So by knowing the value function, this discrete setting, I know for every point where should I move. If I'm here, I should move there. If I'm there, I should move there. So I move downhill gradient. And this is exactly what happens in the Hamilton-Jacob equation. Now, a particular case, and going back again to our linear quadratic problem, and to our quadratic Hamiltonian, we obtain this quadratic Hamilton-Jacobi equation. And if you look at this and you say, well, can I find a solution to this equation? Can I find an explicit solution to this equation? Well, it turns out that you can look for quadratic solutions. You put this in the equation, and then what you do is that you derive this Riccati equation, which is an ordinary differential equation, nonlinear ordinary differential equation, but which has an explicit solution, and you can have some fun deriving the explicit solution to this equation. Now, unfortunately, this is a very special case because in general, Hamilton-Jacobi equations may fail to have smooth solutions, so differentiable solutions. And the reason can be seen by looking at this equation, this Hamilton-Jacobi equation. Let's say I have classical solutions and I differentiate the equation. Then the derivative will solve this equation. This is actually a famous equation in PDE theory. It's called Berger's equation. And now you follow this trajectory. So the idea is that you have this terminal data here. You have a terminal data, and now you follow the trajectory x dot equals v, and v is constant along the characteristic, along this curve. So your trajectory is a straight line. And now the problem that you can see that will arise is the following. You take some terminal data here with some terminal v. In general, there is no reason, because you can choose arbitrary data for this equations. You can choose also data that will go this way, and then this is time, this is space, and then there may be a point where the solution would have to have two different values, or the derivative would have to have two different values, and this shows that you cannot have a classical solution. So key concepts and idea. One is that we have a value function. We have dynamic programming principle. Out of the dynamic programming principle, we can build a Hamilton-Jacobi equation, and out of this, we can have we have a verification theorem, and we have feedback controls. Now, and so far we have been in the world of very classical theory, but of course modern theory of Hamilton-Jacobi equations concerns this issue of non-existence of smooth solutions, and in particular there is something called viscosity solutions, which is a concept of solution that allows you to work with problems where you have shocks or we have lack of smooth solutions, like the example that I've shown before. Now, what is the setting of reinforcement learning? Well, in the beginning, it may seem somewhat different until you realize that it's really, really very similar. You have agents, and these agents have a state and a possible action. For example, you are in a graph, and you can decide go left or right. And then in every state, every action corresponds to a reward. And for example, if you are in this graph, maybe the reward is -1, because you are trying to minimize the number of steps. So every time you move, you have a -1 step, and of course you want to end at some graph where at some point where you can no longer move, and then the reward is 0 forever. So actions change the state according to dynamics. And this dynamics here is going to be deterministic, but we might as well do stochastic dynamics, where you take an action, maybe you decide to go up, but with some small probability you also go down, because people make mistakes, or maybe there is someone confusing you and pointing you in the wrong direction. And And usually in this setting, rewards are discounted in time because the idea is that rewards now are better than rewards later. And what agents want to do is to maximize this long-term reward, which is this series of the rewards at the states and the corresponding actions. But if you look at this, this is a control problem in discrete time. And in fact, reinforcement learning has been used in various problems, and it's the heart of solving Go and chess in a superhuman way, because nowadays these games can be solved, it can be played by machines better than we humans can do. But also things like Google Maps, finding the shortest path, traffic light control, bidding, and even if you look at theorem proving, this is an issue on reinforcement learning, and people have used this kind of things. So, as in Hamilton-Jacobi equations, we have a value function, which in this setting is called the Q function, and we have a discrete Hamilton-Jacobi equation, which is again very similar. There is some kind of Legendre transform, but there is also some discount and some slight differences. So a key problem in reinforcement learning is the following: is that how can we approximate this value function, usually by iterative methods? And for example, a popular method is this Q-learning, which is the following: you are given an approximation of the value function, you choose a state, and you say, well, look, I'm going to build a better approximation by optimized based on the previous guess of the value function. And it turns out that this algorithm is convergent under some conditions, and it's kind of an analog of understanding the long term of behavior of Hamilton-Jacobi equations, a topic that I was quite interested in some time ago. So, what are the key issues here? Well, one of the issues is that the space can be very large. Think of all positions in chess or all positions in Go. So the value function may not be representable in a computer. And you may say, oh, but control on the real line, continuous control, the state is infinite, right? It's uncountable. But there is some continuity. So in fact, if you take a small grid, you can actually represent pretty well a function in a grid, in a continuous function in a grid very well, right? But if you have things like positions of a chess, if you move a piece to the wrong place, maybe you have a losing position immediately, right? And this could happen quite a lot. So what people have been doing are to try to find ways to represent these functions. And one way is to use these feature maps. And this is very similar to what chess players use when you're beginning to learn chess, and they tell you, well, it's a queen is 10 points, a rook is 5, a bishop and a knight is 3, and a pawn is 1. So the idea is that you have some features, and then you try to find out weights. For example, the number of queens or the number of rooks that you have, or the number of bishops, and you try to find some approximation of the value function, and then you try to use maybe Q-learning to improve this value function. So what are the key concepts in key ideas is that, like in continuous control, at the heart of reinforcement learning is dynamic programming and the Bellman equation. We have the Q-learning algorithm, which is one of the important algorithms, but there may be other ways to do it. And of course, some of the key questions in reinforcement learning are how to approximate value functions, how to build training algorithms, and this is something that I'm pretty much interested, because we have very good understanding of Hamilton-Jacobi equations in the continuous setting. Some of these things will transfer, some of these things will raise new questions, and I think that's all I have to say for today. So thank you so much for your attention. If you have questions or remarks, I would be very happy to answer them.
Okay, thank you very much for this nice presentation, Diogo. So we are waiting for questions. if anyone has a question, you can use the Q&A section in Zoom. Okay, if not, we can try to entertain other questions like, so reinforcement learning is unsupervised. Do you think there are connections with supervised learning also in this theory?
It actually depends, right? Because you can, if you're talking about playing Go or playing chess, you can think that it's some kind of supervised learning with data generated by your experiments, right? But one of the common things that you have both in supervised learning and unsupervised learning and reinforcement learning is that you have these functions that are in very high dimensional spaces or very large spaces, and you want to represent them. And because of this, machine learning is a natural architecture. You know, in principle, you could do everything with polynomials, right? Because polynomials approximate continuous functions, so you could do all machine learning with polynomials, very large polynomials. But that doesn't seem to work, and there are good reasons why polynomial interpolations are not chosen to do this. But the properties, the approximation properties of neural networks seem to be better for very high dimensions or very large sets, and they allow to encode some kind of adaptivity that you cannot do with polynomials, for example. So there is a question here: how much insight we have about the transient behavior of performance of reinforcement learning algorithms in light of control theory? Yeah, so thing is, there may be, so one of the things that I'm actually trying to work in my group is different algorithms for reinforcement learning that would have a better convergence properties. Because in principle, from my understanding from continuous Hamilton-Jacobi equations, you may have situations, especially if you're doing deterministic reinforcement learning, you may have situations where you have very slow convergence of this long time behavior of things like Q-learning. So it may be possible to get better algorithms, and this is the thing. So there is another question here. So thank you for the how can we generate the necessary data for this kind of problems? Actually, the data for these problems is for many of these things is simulated. So if you are trying to teach a machine to play chess, you just make the machine play chess. So it's some kind of, a lot of these things is data-less kind of learning, right? So you don't need, if we are talking about things like games or then it's basically simulation based, so you can generate as much data as you want. Can we use control theory methods in optimization? Yes. So for example, one of the things that I've seen recently that has a connection with control theory is what Stanley Usher is doing with the proximal operator. So there are, the thing is that the Hamilton-Jacobi equation, like with a quadratic cost, will converge to the infimum of a function of the initial or terminal conditions. And they have used that to generate algorithms that have good convergence properties. So yes, this is definitely one example. In which service Google is using reinforcement learning? No idea. Sorry.
There's another possible question, which is, we mentioned that you work on mean-field games.
Mm-hmm.
So what are the connections between mean-field games and reinforcement learning?
Yeah, so mean-field games are Hamilton-Jacobi equations coupled with an additional equation, which represents some kind of behavior of population of agents. So there is an obvious connection there that you can have reinforcement learning for multi-agents. So you have a very large class of agents and you'd like to do reinforcement learning on on a wide class, and that's a connection with mean-field games. The other thing is that some of the algorithms that we have been looking at are actually for approximation in reinforcement learning are quite related to mean-field games, because the idea is that we introduce some fake mean-field game, and it turns out that this has nice theoretical properties, which I hope will be transformed into something useful in the near future.